Hi and welcome to All Things Mathematics. In a previous video we looked at rates of change and average rates of change, and some examples showed how we can do that by using the idea of rise over run. Now we can extend that idea to apply it to what we call differentiation, using the idea of rise over run and limits. So let's begin. Rates of change and differentiation. Part 2, differentiation. In an earlier video we looked at the definition of the rate of change of two variables. That means how one variable changes with respect to another variable, and we looked at some examples. And one of them was the one that you can see there on the screen, which is the volume of water poured into a container. You can see that we have a straight line on the right which represents the rate of change of the volume as it fills, and the gradient of that straight line gives us a measure of the rate of change. In this case, the measure of change, the gradient, is found by working out what we call the rise over run. So the gradient is the rise over run, which is 5 over 5, which equals 1. Therefore we can state that the rate of change of the volume of water with respect to time is 1 litre per second. Another thing discussed in the earlier video was the average rate of change. For this example we have the cost per kilogram of tomatoes from the years 2015 to 2018. We can imagine a straight line joining the first year 2015 to the last year 2018. Even though it doesn't cross the image of the tomato for each year, we can still obtain an estimate of the gradient. We can choose 2 points that we are interested in this case, let's say from 2015 to 2018, and connect them with a straight line, and then create our right angle triangle so we can work out rise over run. And there's our rise, $2, and our run is 3 years. So the average rate of change will be rise, which is $3 minus $1, over run, which is 3 years, and that comes out to be a rate of change of 67 cents per year. Now let's get down to the theory. Here we have a curve defined as y equals f of x, and we have 2 points on it labelled A and B. What do you think will happen to the gradient as point B approaches fixed point A? Look at this video. It shows point B approaching point A, and it shows the average rate at each point. Of course, when B reaches point A, what happens? We obtain an average rate of 0.35. So we can conclude that the average rate of change as point B approaches point A at x equals 2 is approximately 0.35. We know that the average rate of change is the gradient, which is given by the rise over run, so we can make a right angle triangle and get an estimate for the rise over run. Now as B approaches A, it is called the average rate of change, but as soon as B is in exactly the same position as A, then we call it the instantaneous rate of change. We can obtain an expression for evaluating the instantaneous rate of change. Let's suppose the coordinates of point A are x and the y coordinate is f of x. If we move a little along to the right on the horizontal x-axis, let's say the coordinates of point B are x plus h and the y coordinate is f of x plus h, as you can see there. The gradient, of course, is rise over run. Now what's the rise from our right angle triangle? There it is. The rise is f of x plus h minus f of x. And the run is h. The instantaneous rate of change is given by what you can see there. Now, LIM stands for the limit, and underneath that, where we have h arrow 0, it means h approaching 0. So what we are looking for is the limit of the gradient as the value of h approaches 0. And that's our definition of the instantaneous rate of change. Can you see why that's true? That as b approaches point A, the value of h becomes infinitely small, and therefore the average rate of change will become our instantaneous rate of change. What's happening here? We have a point on our curve and the instantaneous rate of change at each value. And at x equals 2, the instantaneous rate of change is about 0.36. Notice how this is the same answer as the average rate of change, or the limit, that we saw previously. Let's see how that formula works in practice. Here's a curve defined by y equals x squared, and you might recognise that as the equation for a parabola. And we've got one point marked on it, which is at x equals 2 and y equals 4. Let's obtain our value for the instantaneous rate of change at that point. There's the formula we're going to use. Our function, of course, is f of x equals x squared. F of x plus h means replace the value of x in the first expression by x plus h, and that's what it looks like. And when we expand and simplify x plus h squared, you obtain what's there, x squared plus 2xh plus h squared. And then making the substitution into our formula, that's what it looks like. Notice that x squared minus x squared cancels in the numerator, and that's what you're left with, 2xh plus h squared over h, and that simplifies by cancelling by h, top and bottom, to 2x plus h. So our expression for the instantaneous rate of change now becomes the limit as h approaches 0 of 2x plus h. What that means at this stage is that you replace the letter h by the value 0, and that gives us 2x plus 0, which is 2x. For any x coordinate, its instantaneous rate of change is twice the x coordinate. At x equals 2, the instantaneous rate of change will be 2 times 2, which is 4. Let's see if we can confirm that the instantaneous rate of change of the function x squared is equal to 4 at x equals 2. So we'll go to x equals 2. And there it is. At x equals 2, the gradient, or the instantaneous rate of change, is equal to 4, which confirms what we obtained theoretically using our formula for the instantaneous rate of change. Now here's a summary. X squared, of course, is the one we've just looked at, and the instantaneous gradient, or rate of change, is 2x. If you follow the same formula for, let's say, x cubed, x to the power of 3, you will end up with 3x squared for the instantaneous rate of change. And similarly, if you do that for x to the power of 4, you obtain 4x to the power of 3, and then x to the power of 5 will give you 5x to the power of 4 for the instantaneous rate of change. Do you notice a pattern there? For example, if I said x to the power of 6, what would you say would be the expression for the instantaneous rate of change? We can generalise. Let's suppose our function f of x is x to the power of n. When we obtain the instantaneous rate of change, we will end up with nx to the power of n minus 1. Can you see how that works? Just compare it to the values that we have in the table. F dash x means the derivative of the function x. Or another way of saying that is that we differentiate f of x to get f dashed x. So differentiation means obtaining the instantaneous rate of change. I hope you found this video useful. This is just an introduction to differentiation. Look out for further videos where we will look at more detail at functions that are not just powers of x. Until next time, bye bye.